Since it's going to be a while before we officially see each other again, I wanted to just refine our process for locating these extreme values of functions on their domains. So I made this little list here. Admittedly, I threw it together quickly, but I want to use this to help you get through the current set of problems that we're working on, knowing that we're going to have some new tools soon that'll help us do a better job of locating these things and classifying these extreme values. So what we're going to do for this last set of exercises is follow this plan. So even though this technically is cheating or putting the cart before the horse, what I'd like you to do is go ahead and graph the function first. Look at the graph. You can use Desmos or GeoGebra or a graphing calculator, whatever process or tool that you use to get a graph of a function. But look at the graph and then make a mental note of the locations of the extreme values, the locations of the extrema. And you can tell a lot from the graph before you go into deal with the derivatives. So then once you know where those values are located, then go ahead and use your derivative to locate your critical points, and you can classify those extrema. But you're really just verifying what your eyes have already seen. And I think if you attack the problems that way, it'll take off the pressure for some of these equations that we're working with that are not familiar functions, or functions that have end behaviors with horizontal asymptotes or vertical asymptotes in the middle of the domain, or end behavior that takes off to infinity. Some of those things that we don't have the best strategies for yet. The strategies are coming, but we don't have them yet. For the time being, peek at the graph first, and it'll give you a better idea of what you should be looking for. And then you won't have to worry about limits and things for the behavior, especially with the asymptotes or the end behavior. Let me show you what I mean on another example problem. So this actually is number 46 from our textbook. Not one of the ones I assigned, but certainly similar to some of the problems that you're going to be working on. And notice I plugged this thing into Desmos and took a screenshot, so I have an idea of what this function looks like. Just want to point out a couple of features of this graph. First of all, notice that there is actually a left and right boundary with some vertical asymptotes on this function. And that's because the domain of this function is naturally limited so that the radicand, this piece, has to be positive. And that only happens when x is between -1 and 1. The other thing that I notice is that I have an obvious minimum in this function at 0, 1, at that point right there. And that's actually an absolute minimum. So just by looking at this picture of this function, even though this expression isn't as familiar to me as I would like, as your teacher is familiar to me, but as students you haven't had as much experience with these sort of radical functions. It's okay to take a peek at the graph so that you have an idea of where to head with this. Later we're going to develop some more useful techniques for quickly locating some of these things like the vertical asymptotes and quick ways to classify our critical points. But for right now, peeking at the graph ahead of time is going to get you well on your way to classifying and identifying these extreme values. Just by looking at this graph, I know I'm looking for 1 point, and the answer better be 0, 1, right? We know that from looking at it. Now let me show you how the math supports that. So I essentially just need to locate that critical point that was in the middle of the graph there at 0, 1. The way we locate critical points is we find the derivative. So I'm going to go ahead and do y prime. Now, depending on what your experience is with derivatives, you may want to turn this into a power function with a composition. So I'm going to write it as 1 minus x squared all raised to the -1/2 instead of 1 over the square root of 1 minus x squared, because then I can do the power rule for my derivative. So that derivative is going to be -1/2 times 1 minus x squared to the -3/2. Then by the chain rule, I have to multiply by -2x, because that's the derivative of 1 minus x squared. Oops. That's the derivative of 1 minus x squared. So this right here was because of the chain rule. Now, in order to make this derivative useful, I'm going to rewrite it in radical form. Notice that I have a negative 1/2 times a negative 2x. So that's just going to make an x. So the numerator of this thing is just x. The rest of this is in the denominator because this exponent is negative. And instead of writing this as a 3/2 power, I'm going to write it in radical form. And so on the bottom, it's going to be a square root of 1 minus x squared cubed. I write it that way because it's going to be easier for us to analyze this rational function if it's written this way. Remember that for rational functions, if you want to find out when they equal 0, you simply take the numerator and set it equal to 0. So one of my critical points is just going to be 0. Ooh, that's great news because that's the one that we saw in the graph. Now we should also check for undefined values. And the way you do that is you set your denominator equal to 0. And I can quickly square this thing and then take the cube root, and basically that just means that this equals 0, and that happens at 1 and negative 1, and those are not part of the domain, right? Those are those asymptotes, so we can throw those out. Those aren't critical points. Those were the asymptotes. So I just discovered my only critical point, which is excellent news because that's what we saw in the graph, and then all I have to do is plug that 0 into the function to get the location of that minimum. So it's going to be y of 0, and that's just going to be 1 over 1, which is 1. So we have an absolute minimum at 0, 1. And I've used a combination of taking a peek at the graph and then using the derivative to find the critical points to arrive at that answer. And for now, that's plenty for us. You don't have to go into all the analysis of locating vertical and horizontal asymptotes and checking end behavior and things like that. Let's peek at the graph to get an idea of where these things are and then go through the derivative process to locate the critical point and show that our eyes weren't deceiving us, that in fact the graph does support the math that we've done here. I think that'll make you feel a little less frustrated with these problems that you're working on. So give it a go, and then you know where to find me. If you need anything, let me know. In the meantime, take care.